Okay, welcome back for another installment here in Chapter 11, our introduction to the alkanes. Hopefully, so far things have been going well, and you're interested to see how we're going to complicate things even more. And believe me, we're not going to disappoint you here. So far, we've talked about the straight chain alkanes, and then we complicated things just a bit at the end of the last lecture with the cycloalkanes. Now we're going to talk about alkanes with substituents, and that's a term that doesn't sound so bad, but it will complicate especially the naming when we get to that part of the substituent end of things. So far, hopefully you've done well with the naming. It's been relatively straightforward. And we complicated it just a bit by having to add that cyclo prefix in our cycloalkane discussion at the end of the previous lecture. Now the substituents will complicate things even more, but that's why you took the course. You're up for the challenge, and you're ready to see what I'm talking about here with these substituents. All right, so substituents seems like a simple enough word, right? Let's see what it means for us in this course. So alkanes with 4 or more carbons can have side groups called branches or substituents, right? Before 4 carbons, once we're just 1, 2, or 3 carbons, we're too simple for that. But once we get to 4, we can start to branch, or as we'll come to know them, have substituents. So the substituents are attached to the carbon chain. That means they're going to have to replace at least one hydrogen on that alkane chain in order to make room for that substituent. That's why we call it a substituent. It's substituting a hydrogen with a carbon group. When two compounds have the same molecular formula, but they differ in the order in which the atoms are bonded, they're called structural isomers. And so that's going to cause us to have, again, less reliance on molecular formula because they're the same for these substituted hydrocarbons. But instead, we're going to rely much more so on structural formulas because that will allow us to distinguish structural isomers one from another. All right, so that was a lot to drop in words on that previous slide. Let's look at it in pictures. Here we have the simplest possibility of a substituted alkane, and we get into the idea of structural isomers of butane. So the isomers have the same molecular formula, right? If you just look at it, we would call it butane, and there we have in the top picture the classic straight chain butane, right? However, if we think about the chance for a branch or a substituent, we could have, instead of butane, we could have a propane ring, propane backbone rather, and then we could have a substituent on that middle carbon. Right, and that would cause us to have something that we wouldn't call butane anymore, right? It's not a butane because the butane is the one above that has the 4 carbon chain, which is why we call it but. In the lower case, we have a 3 carbon chain. That's a propane, and now it's a substituted propane, and we've got to come up with a way to name it to be clear about where we're getting our branch, or more formally, our substituent. All right, so there we had it. Those were the 2 different ways we could represent structurally the structures that had that formula, C4H10. Now as we move up just one more carbon into C5H12, what we would have called pentane up until now, based on the rules we've learned, now we have to think about the other possibilities, what we would call structural isomers of pentane. Again, they're isomers because they have the same molecular formula. They're structural isomers because they have different structural arrangements. So we can think, of course, the one that you're probably going to cling to is that straight chain. That's what we've been fooling you with so far, making you think that chemistry is just that simple. And of course, many of you probably came into the course with a little bit of chemophobia, and we're not helping there by making things more complicated already here in the first chapter. But again, in order to understand what you need to understand, for the reason you need to take this course, we do have to talk about the real world, and the real world is messy and complicated, and I try to make it as simple as I can, but I'm not going to sugarcoat it when there's no sugarcoating for it. So here we see the straight chain pentane. That's great. That should be the one you think of first. It's the one I still think of first. But you also have other options. And here what you could do, just like we did for our isomers of butane in the previous slide, we take one of those middle carbons. Can't do it to an end carbon because then we're just changing the way it looks, but we're not changing the actual structure. We're just swapping a terminal group for another terminal group. But if we branch off of one of those middle carbons, that's why we had to get to at least 4 carbons total so that we could have a middle carbon in our previous example with propane, the substituted propane. Now we could pick one or the other. With pentane, or at least a 4 carbon chain now, butane, it didn't matter which one we picked because chemicals don't read from left to right like we do in American culture. So they wouldn't know that that's the way to do it. So if you had pick the other carbon there, the further one, to make the CH and CH3, it would be the same. They're just flipped. That's why I stress those modeling kits. If you build it and you flip it and you see that it would be the same thing, that's why it didn't matter which one we picked. We had 2 middle carbons there in the 4 carbon chain. Whichever one we picked, it's identical if we had picked the first or the second because we could just flip the thing around. The other thing we could do is we could take that middle carbon, we could make a propane and take the middle carbon and have a CH3 group coming off both the top and bottom as it looks on this flat representation. So now we have 2 different branched alkanes that we could make with that same formula, that same C5H12 molecular formula that the straight chain pentane would give. So we've got 3 structural isomers with that same molecular formula. Since you don't have a lot of time, I would imagine, for this sort of thing, we'll stop there with our examples where we do them one by one, because as you see, we already talked about it, 1 carbon atom, we can only have the one thing. So if it's an alkane with 1 carbon atom, it's methane. There's no other structural isomer with that CH4 molecular formula. Same deal for ethane, C2H6. There's no other way to do it. Propane, C3H8, that's it. Once we got to butane, that's where we saw we could make a propane that's substituted on that central carbon and we had something new and different. When we got to pentane, we now could substitute just once off a butane chain, or we could substitute twice off a propane chain. And so we built up. If we were to keep doing this, it gets exponentially more complicated as we increase the number of carbon atoms. So 6, that wouldn't have been so bad. We could show hexane, and then we could show the 5 other structural isomers. We go to heptane. Now we've suddenly got 9 structural isomers. I'm sorry, there would just be the 4 structural isomers and the hexane in the case of number 6. And for heptane, there would be heptane itself and then 8 structural isomers. Once we jump to octane, now we've got 18. Nonane has now 35, and decane has 75 isomers. So that's one reason organic chemistry is so important, because the structure is so critical. We have to know what atoms are and where they are in a given organic compound, because we have such a diversity of compounds that we can make with those same building blocks. And remember, this is just carbons and hydrogens we're talking about right now. Imagine when we throw oxygens and nitrogens and phosphorus and sulfur in there. It gets very, very complicated, and that's why you and I, as human beings, we're made up of these millions of different biological compounds that are largely organic based, because just changing the number, the types of atoms involved has huge impacts on the biochemistry that they're able to accomplish. So this is a good thing, right? It's great that things are this complicated because it explains how we can be so complex and so interesting. Okay, so now that we've expanded your thinking a bit, let's see how you can handle that new knowledge with a learning check. So in this case, we're going to identify each pair of condensed structural formulas as structural isomers or just the same molecule over again. So for A, B, and C, you'll look at the 2 structures represented in each of those cases, and you'll decide whether or not it's truly something new and different, or it's just another way of writing the same thing. So just say same or different. You don't have to worry about naming them. We'll spend lots of time on getting those naming conventions down. Pause the video here if you haven't already finished that, and then start us back up once you're ready to check your work. All right, so hopefully you did well on these. For A, that was the example we showed with butane and then that substituted propane. So those were really different. They're not the same thing, and they are therefore structural isomers. Likewise with B, we had the cycloalkanes hexane compared with the substituted cyclopentane, right? The cyclopentane has that line off it, which would indicate there's a CH3 group at the end of that line. So they are the same structural formula, the same molecular formula rather, but different structural isomers. And then finally with C, we have the same molecule over again. We've just drawn it in a way that makes it look different, but ultimately it's a CH3 connected to a CH2, connected to a CH2, connected to a CH2, connected to a CH3. We've got free rotation around all those single bonds, and we've just shown it in a rotated form. So be careful, not everything that looks different is different. That's why those skeletal structures are so nice. They're very clearly different here, and if you're following the rules for drawing the structural isomers using skeletal structures, they should very clearly be different, whereas the same molecule should look the same, aside from where we talked about that judgment call at first. If you start up and draw down, or if you start down and draw up, you can get slightly different images that are the same thing. All right, I think I've already used the term without defining it, shame on me, but alkyl groups. So alkyl groups are carbon branches, and they're named by replacing that A and E ending that we've talked about so far for the alkanes with the corresponding alkane name and a YL ending. So I know I dropped this methyl name earlier, and I apologize. I think it was as recently as that learning check, but methane would be the CH4. Methyl is a group that's a CH3 bonded to something, right? That something is not a hydrogen, otherwise we just call it methane. It's another carbon group. So we see there in that first example, we have a methyl propane, a propane with a methyl group on that central carbon. And then we see down below, we have methyl group on the second and fourth carbons of that pentane. So that's our methyl substituent. Ethane gives us an ethyl group, right? It's just that simple. We're just taking off one of those CH bonds from a terminal carbon and replacing it with a C dash, which can then be bonded to another carbon on a different alkane, for instance. Propane becomes a propyl group, and so on and so forth. So we can go all the way up. It's rare that you'd have something like a decyl group, but it could happen. Or decyl, as it's probably more commonly called, at least in the British-speaking, English-speaking world. So just be aware of that. Just because you think you have a long substituent, you may need to rethink the longest carbon chain. So be careful about that. That's another way things get complicated here in organic chemistry. And while we're complicating things, let's go ahead and throw in heteroatoms. When I say heteroatoms, I mean something other than a carbon or a hydrogen. So halo groups are an example of heteroatoms. So they're halogen atoms attached directly to the carbon chain, or the carbon ring, as the case may be. And they're named just like the halogen, only you take the root and put an O ending. So instead of fluorine, you say fluoro. Instead of chlorine, you say chloro. Bromine becomes bromo, and iodine becomes iodo. So there you have it. There's the four typical halo groups, and we see there's example where we have the carbon-bromine bond. That's very common in fire retardants. They're often brominated, where you have a carbon-bromine group. Likewise, you can have a chlorinated group there, as we see down below. PVC, polyvinyl chloride, is a very ubiquitous example of a plastic with a chloro halo group attached. Okay, so if we pause here to look at table 11.5, we've got the names and formulas of some common substituents. As I said, the most common alkyl substituents will be short ones like methyl, ethyl, propyl. Isopropyl you see is different than propyl. They're both 3 carbon substituents, but the isopropyl, it's almost like a pair of scissors. It's that center carbon that attaches to the alkane chain in this chapter, whereas the propyl group attaches at a terminal CH3. So just be careful. That's the difference there. 2-propyl is another way to say isopropyl, although you'll commonly see it isopropyl because you'll see a lot of mix of IUPAC and common naming in organic chemistry in particular. And then finally, we see the halo groups we just talked about: fluoro, chloro, bromo, iodo substituents. So these are the ones we're going to run into most commonly here when we're still dealing with alkanes. When we move on to things like alcohols, then we'll have oxygen as well, and we'll deal with that when we have to. For right now, we'll keep it pretty simple, just the select halogens and the carbon groups. All right, so if you took Chem 141 online with me, then you're no stranger to these guides. If you didn't, then depending on what text you used, if you at least used the Timberlake text that we use, then you've seen these before because they're in the textbook. But if you're brand new to them, they're something that I think is helpful. It's good for the student to have the text correspond with the notes, in my opinion, and so therefore we use them here as well. And so they're trying to simplify things by giving you a few key things to look for. So hopefully that works for you and it's helpful. So in this case, we're looking at how we name these alkanes with substituents. Naming has been easy so far, right? Nonane, decane, no problem, hopefully. But now we're going to complicate things quite a bit because we have to. It's, that's not anything I want to do. I'd love to keep the course nice and easy and just be filling in A's at the end of the semester, but you've got to earn the A's now, right? So the way you'll earn them is by keeping track of things like these rules. So in our guide to naming alkanes, we'll write the alkane name of the longest chain of carbon atoms. So we don't have nonal substituents on propanes, we have propyl substituents on nonanes. So just be careful about that. That's why we tend to see common substituents being small, like methyl, ethyl, propyl, or isopropyl. We don't tend to see really long chain substituents because they're part of the alkane name of the longest chain of carbon atoms. Number 2, we'll number the carbon atoms starting from the end nearest to a substituent. And if we have multiple substituents, we'll want the lowest sum of those substituent numbers. Then finally, we'll give the location and name of each substituent in alphabetical order as a prefix to the name of the main chain. All right, so the guide may not seem so instructive in generic terms. Let's take a look at this in the real world with some real examples. Okay, so here we have an actual example, an alkane, right, with alkyl substituent. And step 1, write the alkane name of the longest chain of carbon atoms. So we see the longest chain is going to be 5 carbon atoms long, and that's going to be a pentane. All right, and so there we have the way we could do it. We could also have skipped that first CH3 group and started at the down CH3 group and gone over. That would get us to the same place. So oftentimes you'll see that. Sometimes there is a difference depending on where you start, and don't be afraid to start at what we would consider the end, the far right. Sometimes is the right place to begin, even though in standard American English we read from left to right. Step number 2, number the carbon atoms starting from the end nearer a substituent. So there we have it. That substituent shows up on the second carbon in if we start at the left. So in this case, we're doing things very traditionally. Don't let it fool you, because sometimes we will go backwards compared with standard American English conventions. All right, now here we are in step 3. We're going to give the location and name of each substituent in alphabetical order as a prefix to the name of the main chain. So based on our numbering and when we hit the substituent and the fact that in this case it's a methyl group, we're going to end up with a 2-methylpentane. Notice the 2 is separated from the name by a dash, and then the methyl substituent is not separated at all from the name of the main chain pentane. There's no space, there's no dash, nothing. All right, so there we have it, naming an alkane with a substituent. Hopefully not too bad. Hopefully something that you're comfortable with, or you'll do some practice to get yourself there, and you'll also stick with us because it gets more complicated. So we gave you a relatively simple one, and I'll try to keep things as simple as I can, but I also have an obligation to show you what's out there because you're taking this course for a reason, and we want to make sure that you're ready to see whatever you might see, whether it's in the health professions or in engineering or wherever you might be headed. So here on this slide, we see a couple other examples of methyl substituents. So we have methylpropane. Notice we don't have to call it 2-methylpropane because there's no other place to put it. If we put a propane group on carbon 1 or carbon 3, we'd just be making a butane. So we don't have to say 2 because methylpropane has no other option. If we look down below, now 2,4-dimethylpentane, the 2 and the 4 tell us that there's a methyl group on carbon 2 and carbon 4. We do have to specify those because there could be a methyl group on carbon 3. There could be 2 methyl groups on carbon 3 for that matter. So that's why we have to give both the numbers 2, 4 and the di to indicate that there's 2 methyl groups. We could also have 3,3-dimethylpentane or 2,3 or 3,4. There's other possibilities, as we saw in that table, that things get complicated pretty quickly with a relatively small number of carbon atoms in our course. But in this case, it's 2,4-dimethylpentane for that particular structure. All right, here it is. Your turn to show me what you know. Our first learning check on naming a substance with a substituent. So what is the alkane name of the following structure? So we see the structure there. Please let me know what the name is for that structure. Pause the video here. Start back up when you're ready to check your work. All right, so I broke it down a little bit. So what is the alkane name of the following compound? Well, step 1, first we'll write the alkane name of the longest chain of carbon atoms. So that was 4 carbons, whether you started at the top and bent to the right, or whether you just took the more typical approach and went along the entire straight chain there along the bottom. Either way, you end up with 4 carbons with a substituent on the second carbon group. So number the carbons starting from the end near a substituent gives us carbon 2 with that methyl group. All right, moving on to step 3, give the location and name of each substituent in alphabetical order as a prefix to the name of the main chain. Well, this one was fairly simple because, again, it's a 2-methyl group example, in this case 2-methylbutane. So things haven't been so interesting or exciting yet, but don't worry, we're going to get there. Hopefully this was nice and easy to come up with 2-methylbutane as the answer, but don't pat yourself on the back or get too smug too quickly, because you are going to have to work a little harder as we look at some more of these examples. All right, so now let's talk about naming the haloalkanes. So in a haloalkane, halogen atoms replace hydrogen atoms. We already mentioned that. Substituents are numbered and arranged alphabetically. And be careful about that. Alphabetically doesn't necessarily mean, right, that fluorine would be first because it's the first halogen. We do it in alphabetical order. So chlorine before fluorine, bromine before either of them, and then iodine at the end there. So substituents are numbered and arranged alphabetically. Alkanes with halogens can be named as alkyl halides. The carbon group is named as an alkyl group followed by the halide name. So here we have IUPAC name for these two substances, chloroethane and bromomethane. But the common name that you'll often see, probably more often than the IUPAC name, ethyl chloride and methyl bromide. So be careful. We try to do everything in this course by IUPAC name, but some of these common names are so persistent because they've been in use for over 100 years. People like them. They're used to them. The older chemists pollute the minds of the younger chemists, and we propagate these common names when ideally IUPAC would take over. So just be aware that you're going to see common names more often than you'd probably like, certainly more often than I'd like, but it's just a fact of life. The common names are in common usage. IUPAC names are sometimes not used very often at all. So up until now, I've done an example, and then I've asked you to do a learning check after. This is our first time where we're going to put you out there. Let's see how you do on your own. This is a haloalkane, and we have not seen an example of that. I haven't named one for you yet, specifically, aside from showing you the example there for chloroethane or bromomethane. And this particular learning check has both a methyl substituent and a chloro substituent, so you get to deal with that too. But that's good. You're ready for it. I want to see how you do with it. So in this learning check, you're asked, what is the IUPAC name for the following? And you're going to go ahead and wow me with your skills here. Stop the video so you can come up with this name, and then we'll check. And I'm hoping we're going to have the same name on the screen when you're ready to start up again. All right, welcome back. So looking at our solution, step one, write the alkane name of the longest chain of carbon atoms. So there's 5 carbon atoms, whether we start at the top right or we start at the extreme right. Either way, we get to 5 carbon atoms in our longest chain. So this is a pentane. Step number 2, number the carbon atoms starting from the end nearer to a substituent. So either way, we're numbering backwards. We're going from right to left, which is not typical for the way we read, but it is very common in chemistry. That's why I warned you not to get attached to left and right and up and down, and also why I strongly advise that you pick up a used modeling kit so you can build a lot of these things and prove it to yourself. Okay, so far so good. Let's hope things continue as we move on. All right, now finally in step 3, we're going to give the location and name of each substituent in alphabetical order as a prefix to the name of the main chain. So be careful. That alphabetical order is probably what caused any of you trouble who may have had some trouble on this, because it means that the chloro group comes first, even though it's numbered higher. So this is a 3-chloro 2-methyl pentane. My guess is there's probably a number of 2-methyl 3-chloropentanes out there, and hopefully not too much else. But I can completely understand why you might want to go with the 2 before the 3. But remember, the rule is naming goes by alphabetical order of substituent, not number of substituent. So it's one of our conventions that you just have to get used to. The problem with naming is it's not like data where you can say that, you know, this is good or this is bad. Naming is human convention. This is what we've all agreed on as chemists, and most of us had no say in it because it was agreed on before we were even born, but this is the way we do it. So you've got to get with our program. Unfortunately, there's no other option for IUPAC naming but to follow these conventions. Okay, so hopefully you did well. I'm guessing a few of you, like I said, may have had 2-methyl 3-chloropentane, but that's a relatively easy fix. That's just getting used to the convention. If you're totally lost, please do try some additional naming questions and reach out to me for guidance. Let me know exactly where you're having trouble, and we can hopefully get things squared away for you. Let's follow up with another learning check. In this case, you're going to give the IUPAC name for each of the following, and here hopefully if you had any trouble in the last one, you'll be able to find a way to name these correctly, learn from those mistakes. If you haven't had any trouble so far, hopefully you'll continue to breeze through this IUPAC naming exercise. Please pause the video here while you complete your work of naming these structures, and then start it back up when you're ready to check your work. All right, I didn't break these down into the individual steps because hopefully you're getting the hang of those steps. If that's not the case, please do try some more problems going step by step. But if you're already comfortable with those 3 steps to approaching the names, then hopefully you also were able to come up with the correct names, which in this case was 2,4-dimethylhexane for A, and then for B, 3,5-dichloro-3-methylheptane. All right, and I've shown the numbering scheme at least, and why we selected the prefix of di there for the chloro, and why we went with 3 versus 5. We went with the 3 for the carbon that had the chloro and methyl substituent, so that we ended up with the lower sum overall, right? We would have hit a chloro substituent if we went from left to right, numbering number 1 at the extreme left, so on and so forth. We would have had still 3,5-dichloro, but then we would have had a 5-methylheptane, and we want the fewest, the smallest sum from those. So here we're able to get 3 plus 5 plus 3 is 11, whereas if we had 3 plus 5 plus 5 is 13. So that does come into play here. If that was not something you were aware of, I can certainly see why you would have missed letter B, but hopefully now you know that that's part of the game, and you'll be on the look for that in the future. So far, all of our naming has been with straight chain alkanes. Now we'll talk about naming cycloalkanes with substituents. And it's not much different when naming a cycloalkane with a substituent. The name of the substituent is placed in front of the cycloalkane's name, and the number of the substituents not needed when there's only one substituent, right? They're essentially the ring, every position's equivalent with just one substituent, but once we get multiple substituents, if we have two or more attached, the ring is numbered by assigning carbon 1 to the substituent that comes first alphabetically. So alphabetical order so far has trumped anything else. So we want that alphabetical order gives the carbon 1 assignment. All right, so let's take a look at this. So we've got the name of the substituent placed in front of the cycloalkane name. So in the first case, we have a methyl cyclobutane, right? It's a methyl group, and it's attached to a cyclobutane. It doesn't matter which carbon number that is, because any carbon that we attach that to, we could rotate the structure to look the same. Now, in the second example here on the slide, we have two substituents. So we number the ring as 1-bromo-2-chloro cyclopentane. Why did we pick number 1 for bromo? Because bromo comes first alphabetically. So be careful, that's the rule, and just be on the lookout for it. So when we have multiple substituents, we do have to number, and we're always looking to number where we get the smallest number for the alphabetically first substituent. We will also have cases where we have to, consider numbering like we did in that one example that you worked on the learning check, where there may be a difference if you number 1, 2, 3, 4, 5 clockwise versus counterclockwise, and we want still the lowest sum in that case as well. All right, now that you're all masters of naming from structures, we've got to be comfortable going the other way. So here's our guide to drawing alkane structures from a name. So number 1, we draw the main chain of carbon atoms. Actually, it's better to have the name, in my opinion, because at least the name already tells you what the longest chain is, and you can always draw the longest chain from left to right in sort of a straight line type fashion if that's what you want to do for a condensed formula. Number 2, we number the chain and place the substituents on the carbons indicated by the numbers. It's all there for you to interpret. And of course, we're talking about chains, but the same would be true of rings. And then finally, number 3, add the correct number of hydrogen atoms to give each carbon atom 4 bonds. So we never really worry about hydrogen. We just figure there's enough hydrogens to make everything, in the case of alkanes, everything saturated. All right, so let's look at that together. The structural formula for being drawn from the IUPAC name, in this case 2,4-dimethylhexane. Well, the first part, the 2 and the 4, tell us the locations of the branches on the carbon atoms. The hexane, which is probably what you looked at first if you followed my guide there, the hexane tells you it's a 6-carbon main chain with all single carbon-carbon bonds because it's an ANE and an alkane, everything's saturated. And then finally, the middle there, dimethyl, tells us that both of those substituents are methyl groups. So we can go ahead and draw our 6-carbon chain. We can put a methyl group at position 2 and another methyl group at position 4 and complete everybody else with hydrogen so that everybody has a total of 4 bonds for each carbon. That's all there is to it. Hopefully it's not very difficult, and if you survived naming from a structure, getting the structure from a name is not bad at all. All right, so after that brief little look at taking a structure from a name, let's see how you do on this learning check. In this learning check, you're asked to draw the condensed structural formula for 3-bromo-1-chloro-butane. So please go ahead and pause the video here while you work, and once you're done with your work, please start us back up so that we can compare our answers. All right, so if you're following our guide, and since that's the way the text does it and the way I'm doing it here, hopefully you are following that unless you have a reliable way that always works for you already. So step number 1, draw the main chain of carbon atoms. So I'm looking at the very end of the name to see it's a butane, so that tells me I have 4 carbons connected in a straight chain fashion. Number 2, number the chain and place the substituents on the carbons indicated by the numbers. So I have a 3-bromo, 1-chlorobutane. And again, the reason that it's a 3-bromo, 1-chloro instead of a 2-bromo, 4-chloro has to do with those numbers, right? 3 plus 1 is 4, whereas 2 plus 4 is 6. So just be careful about that. Finally, if you go ahead and add the correct number of hydrogen atoms to give 4 bonds to each carbon, we end up with the structure below. So hopefully that condensed structural formula was not too bad to interpret from the name. And hopefully if you're really wanting to check and gauge how you're doing in the course so far, try drawing these as skeletal structures and see how that goes for you. Hopefully you are always practicing getting yourself comfortable with those skeletal structures, because you're going to see those a lot, especially as we move into biological chemistry where we have long chains for our structures. All right, this has been quite a little topic, so let's follow up with another learning check. And in this case, you're going to name each of the following so that we make sure you don't neglect your naming skills. So in the last case, you interpreted a name to draw, and now you're going to interpret these drawings to find a name. Please pause the video here while you do your work and start back up when you're ready to check that work. Okay, so hopefully this was pretty short and simple. For number 1, that's clearly a cyclopropane, and so therefore we're looking at a methyl substituent. Since there's only one methyl substituent here, we don't have to number it because any position on the ring is equivalent. So we have a methyl cyclopropane. For number 2, things were a little more complicated because we did have the 2 substituents, but if you remember your rules, we number in such a way that we have the lowest overall numbers. So chloro group will number as number 1 because it's the alphabetically first compared with the ethyl. And we number backwards around the ring to get 1, 2, 3 for the position of the ethyl group, because if we look at the cyclohexane and we numbered clockwise, where we'd go 1 for chloro group carbon and then 2, 3, 4, 5, well, 1, 5 would be a total sum of 6, whereas 1, 3 is a sum of 4. We go with the lowest sum when numbering. So that's why we end up with 1-chloro, 3-ethyl cyclohexane. All right, hopefully you were able to arrive at both those correctly. If not, hopefully you're able to understand now why you got them incorrect if you did, and you reach out to me for help if it doesn't get better after trying a couple more examples. I know it's still early on in the course, but this was a really involved lecture, so let's do one more learning check before we leave this topic. And this time you're asked to write 3 isomers of C5H12 and name them. Okay, so hopefully you have caught on to what these structural isomers are all about. Take a few moments, stop the video here, write those 3 structural isomers and give their names, and then start back up once you're ready to check your work. Good luck. Okay, so there we have it. The one that hopefully came easiest to you was the straight chain pentane, right? The 5 carbon atoms in a straight chain as a saturated alkane. That would be the one that came to me easiest. Hopefully it was the one that came to you easiest as well. And then it's a matter of taking those carbon groups and putting them on different positions of shorter chains. So if you decrease the length of the carbon chain by 1, take away one of those methyl groups and put it on one of the 2 central carbons, now you end up with butane that has a methyl group in position 2, whether you chose the second one in from the left or the third one in from the left, it would still end up being a 2-methylbutane because we'd number at the carbon that's closest to the substituent. And then finally, if you decrease the carbon chain length to 3 carbons for a propane and take that center carbon and put 2 methyl groups on it, that's the other structural isomer of the C5H12 formula. And so we end up with 2,2-dimethylpropane. So hopefully coming up with those structures and their names has become quite easy at this point. If that's not the case, then please do practice some additional problems. reach out to me for help, or at least to find some more problems if you've exhausted the end of chapter questions. But otherwise, if things are going well, we'll see each other again in the next section.